Swayam Prabha. Digital India. Educated India.
Welcome back. So let's continue the discussion on the non-premixed combustion, where we are doing the discussion of the mixture fraction based basically the conserved scalar kind of approach. And what we have looked at it when we have a equilibrium assumption, and then we solve the mean flow field, and through there we assume the PDF shape or the probability density function. And at the different location in the domain you have a different probability, and then from that, using the local flame structure where we assume the equilibrium assumption, that means fuel, oxidizer, temperature, all these would be strictly function of the mixture fraction. And also we have looked at that example from a perspective of a single chemistry, and then using that local frame structure along with the PDF we get the mean profiles, like for temperature, species mass fraction, like fuel and oxidizer, and then the connection between the Eulerian flame or the mean flow field is done through the density. And that is where we stopped, and now we will quickly go through the elemental mixture fraction, which is for a detailed chemistry. And then from the elementary mixture fraction, so that is what we have already looked at it. You have each species is composed of some element COHN. Then at the element level you can define the elemental mass fraction like this, and the elements are not destroyed by chemical reaction, the mass fractions also can be obtained. Now then for this we can normalize it actually. For this both the streams we can normalize the mass fractions using that, and then finally what you get the unnormalized mixture fraction, which is written in terms of carbon atom, hydrogen atom, oxygen atom, nitrogen atom, and this is how you get the mixture fraction using those unnormalized mixture fraction. And then you use this Bilger's information to get these things. So this is how you can, using the elemental concept also you can find out these things. Now moving ahead, we already have looked at this, where you have a single step chemistry, it could be reversible or non-reversible, and then if we just consider the reversible case, you have two limits. One is the first chemistry limit, where it will immediately becomes equilibrium. That means what will happen at the stoichiometric, all the fuel will get consumed and oxygen will also get consumed, and you will get the maximum temperature, which is becoming independent of strain. And this is strictly for irreversible reaction with the first chemistry limit. That means if I look at my fuel will, from there the fuel will become 0 here, oxygen will become 0 there, and the temperature will go up. At the same time, if you have a finite rate chemistry limit, which is a non-equilibrium situation, and K will less than infinity, the temperature, this is the peak which you get from the infinitely fast chemistry assumption, and these are the situations where you get the finite chemistry for low strain and finite chemistry, and you can see the temperature profile goes smooth and showing some sort of a curve. This is a representative curve. Exact value can be obtained for a particular fuel using a particular strain rate. One can get this information. That is not an quite difficult to obtain. One can write a small few lines MATLAB code and even get that thing. Now, when you use the reversible situation, you can see even the equilibrium limit where the first chemistry assumption is there, the temperature does not go peak, it takes a smoother profile. This is still independent of strain, and then when you take the finite rate effect for different strain condition, you see the profile variation. And one important thing to be noted here is that the infinitely fast chemistry limit, which is an equilibrium limit, always produces the maximum temperature, and when you have actually strain effect, that means the realistic flame, they do expose to the strain effect, there actually the temperature comes down. Now, if we, this is a situation where your fuel plus oxidizer to product, this is a infinitely fast one step reaction. So, if we complete the equilibrium flamelet model, this is what we solve, the mean flow field and along with the turbulence information. So, this could be Rand's equation for the turbulence model. It could be k omega, realizable k epsilon, it could be anything, not necessarily it has to be k epsilon. And then using this information, the mixture fraction and variance, we can estimate the probability density function. So, this is an presumed shape PDF. So, this you obtain, and from the equilibrium limit you have all this information like oxygen, fuel, temperature, they are strictly function of Z. These two you combine, get the mean profile. Also you can get mean profile for fuel, oxidizer, and also you obtain the density. This is an important term because this is actually, this is our, if you look at it, this side, so that is the density is the term which actually, and also if you have a temperature dependent viscosity and diffusivity, they make the handshaking between this mean field equation to the flame structure or local flame structure. So, what you can see, that means it sort of split it in two different segments. One you said okay, it is only mixing control and you solve for all this, and then using the local information of the flame structure with the presumed shape of the PDF, we close these terms and the mean profiles, density and the transport property, which will again go back and be used in this mean flow field equations, where mean density, viscosity and all these are used. So, that is how there is a back and forth information sharing takes place and the whole calculation progresses. Now, our equilibrium model, which is an situation where you have k equals to infinity, that means it is an where fuel gets burnt, a oxygen gets also burnt, there would be temperature peak. So, that is everything is sort of, and this is our ZST, this is fuel, this is OX and this is temperature. So, they get actually burned and you can see this thing, this is now the whole thing, it is split it in two problems. First one is the mixing problem of ZX, where ZX and variance the transport equation is solved, and second is the lookup problem from equilibrium state given X. That means this local flame calculation, one is the mean field calculation and is the local flame structure calculation. So, when in the local flame structure you have this information where your temperature would be the function of zx, and your mixture fraction is also going to be the function of zx. So this again works provided if it is only two stream problem, this works very nicely. There is no problem and it's quite fast because it's a simple approach and the equilibrium calculation is quite simple, and you can have a table to be ready. It does not take into account the radiative loss, but it is a infinitely fast chemistry assumption and equal diffusivities. So the conditions which one can relax is that you can introduce more than one mixture fraction. So this can be applied to more than one mixture fraction if we define. So right now instead of that, if we say Z1 and Z2, then we can easily solve 3 stream problem, where first 2 stream will interact with Z1, second 2 stream will interact with Z2, and total Z would be function of Z1 and Z2, like that. Now we can add also enthalpy in this, enthalpy deficit rather, as an independent variable. So that will take care of this radiation issues and all these things, and we can generalize this. Now when you look at this flamelet equation, what we do, that is the step 1, how we go about it, step by step process. Now we have transport equation, and the transport equations are defined in this x1, x2 and x3 coordinate system. This is our global coordinate system. Now what is that? A change of independent variable is made, which is like that the z, which is a function of this, and the we make it to other coordinate. So if we look at the flame front, this is the fuel, this is oxidizer, and this is jet stoichiometric. So in the flame normal direction there are local coordinate system one can define like this and this. So the local coordinate system with the first axis orthogonal to the flame front, increasing z, and the other coordinate orthogonal to first. So this is how with the increasing z we can see that, because z is sort of 0 here, z is 1 there. So this is the 2 coordinate system that we define. So that means we have a global or Eulerian coordinate system. From there we go to this local coordinate system in the flame front, and that is why we keep on emphasizing this one is the frame normal kind of analysis. That means there is a transformation which takes place. Okay. Now this is the coordinate system, or the I would say local coordinate system which is been defined along the flame surface. Now we transform the species mass fraction equation. So the unsteady term will be there, then this is the velocity in that local transport coordinate system, delta in the local coordinate system. There will be a term which is there, the diffusion of the species in z with respect to z. That means along this how this guy is actually varying. So what can think about it, instead of looking at the mass fraction equation in different 3 coordinate system, now we are trying to write the mass fraction equation in a single coordinate system of this, then reaction source term, and we will get the other extra term like this, this and this. So diffusion in the z direction can be determined by the scalar dissipation rate. So this is how we define chi equal to 2d del z by del x. So this is a connection. If you see, this is the term which actually a function of spatial coordinate or the physical coordinate, which connects this transformation equation with this z coordinate system or the local flat coordinate. but here one important thing, that the equal mass diffusivity is assumed. So similarly, one can transform the temperature equation too. That means from your this system to other system, so we get mass fraction equation, we get temperature equation, which are transformed to, so now they are in Z and time. Now in the step 2, so we neglect some terms. So we neglect the terms which is parallel to the front in the species transport equation. So if these are parallel to the front, this term cross out, this term also goes off, and this term also goes off, and what we end up getting it, the unsteady term of the mass fraction and diffusion term and the source term, chemical source term, and where scalar dissipation rate chi becomes a function of Z, or rather it is a function of Z and local, the global coordinate system, or the coordinate system where the mean flow field are solved. Now the Flamelet equations which one can be solved, which is a function of Z, and this for important value of scalar dissipation rate at stoichiometry. So that is what you get. That means you see, this is what after transformed, this is what we get. That means our species mass fraction equation and temperature equation, these are transformed to the local coordinate system or in Z coordinate system or function of the Z. So this transformation, that is why it is along the flame normal direction. This particular analysis is known as flame normal analysis. Now you get two set of equation, one is for individual mass transfer equation and second is the temperature equation. Okay. So both of them, now this is for a steady case, and if you see that the unsteady term is gone. Now here this is the term, the scalar dissipation rate, which is a function of Z and local spatial coordinate system or the global coordinate system. So there is a connection between our Flamelet equation or the flame normal coordinate system information with the global physical coordinate system information, because Z is also evolving in the physical coordinate system and scalar dissipation is calculated from that, and that scalar dissipation rate is connection between our. So this is what you can think about the local flame coordinate to connected with the scalar dissipation with the physical system, physical coordinate system. Okay. So this connection is important, what it is doing. So if I look at from the computational point of view, this is less demanding than 2D or 3D simulation, and detailed chemistry one can use, and this is while solving the mass transfer equation one can incorporate the detailed chemistry and reaction rate has to be calculated. But importantly, this is not done on the fly of the calculation. So this is done in the pre-processing state. That means these calculations are a priori done, and then a lookup table has been created which is stored there, and the information is fetched out from there. Now profiles of species and temperature versus mixture fraction and scalar dissipation rate as a parameter, which are obtained by solving this set of equation. Now when the scalar dissipation rate is low, that means it tends to 0, which means the equilibrium limit is approached. If this is high, then one can expect to have extinction and there will be only mixing without any combustion. So there are two different limit of scalar dissipation rate. Now alternatively, one can have an calculation of the local structure without making the transformation of the flame rate equation. And how can that be done? You have a fuel and oxidizer, and this is how the reaction flame front would be, where the Z is, this is Z stoichiometric line. And if you look at a situation where the instantaneous flame front, and you can assume like in fuel and oxidizer, they are actually coming from the opposite side, that means a counter flow configuration, from where you can get this stagnation point laminar flame, and that may be used here. Now this steady laminar counter flow diffusion flame, here this is our oxidizer, this is how fuel is coming, this is the coordinate system x and y, and this is where the flame is sitting there, and this is the stagnation flame. Now the assumption is that u is function of y and steady state solution along y axis. So we get this equation, we get this equation, then we get mixture fraction equation and species mass fraction equation. Now this particular one can, that means the mixture fraction equation can be replaced by the Bilger's formula. So that is one possibility of looking at it, that one can do that. And secondly, the pressure can be correlated with the strain and the density. So this is the axial pressure which is sitting there, can be obtained. So without transforming the system, we can actually write down the system in this fashion. Now you can solve this counter flow diffusion flame equations. This is computationally much less demanding than a 3D or 2D DNS or detailed chemistry. Now the profiles of species mass fraction and temperature as a function of distance y, these are obtained. And what it does, it solves the full set of species equations which are solved. Detailed chemical models are also used, so that means detailed kinetics and all these things can be invoked. And then Lewis number 1 or equal diffusivity is not necessary, strain rate is specified, and scalar dissipation rate is calculated as a part of the calculation results. So a dedicated solver which actually does this kind of calculation like OBDIP, Cantera, Chem1D or Flame Master, something like that. So these are the available one which one can use. Now if you look at the spatial profile of scalar dissipation rate in the counter flow diffusion flame, so this is the jet stoichiometric line, and this is scalar dissipation rate, and this is how it varies. This is the reduced y, and that is the position of the flame, and this is how this varies, the scalar dissipation rate. So that give you an idea, and this is fuel and oxidizer is coming from opposite side, that is why it is called a counter flow diffusion flame. Now there are different profiles which are available that to represent the scalar dissipation rate. Let us say for case with constant density, profile versus distance is given as zy is half of 1 minus error function, and scalar dissipation rate is a by pi exponential function of a by d y square. So this is for a constant density situation, and the profile for scalar dissipation rate as a function of mixture fraction is given as a by pi exponential minus 2 error function, inverse error function of 1 minus 2z, which is nothing but z max a chi max and fz. And similarly, you can find out the stoichiometric scalar dissipation rate, which is A by pi this. This is also chi max and function of z stoichiometry. So this is what one can get for different profiles. Now you can look at the construction of a flamelet library from laminar counterflow diffusion flames. You have a fuel jet coming in, you have air coming in, and this is what the burn gas. So first thing that it's all 1D profile along the center line axis, and where you can see the variation of the species, mass fraction, temperature and all this. So a set of laminar opposed flame diffusion flames are calculated, and then the profiles are stored in a library. So that is important. That's why I said these things are done at the pre-processing stage. So it is not what is usually takes place at the during the calculation. Then it depends on the characteristic straining of the flame, that A or stoichiometric, and then you assume the profile for T and Z. So now if you see the flamelet model for non-premixed combustion, which is an adiabatic one, that means there is no heat loss. So the problem essentially split into two problems. One is mixing problem, finding Z, and then the chi stoichiometric, and then lookup table problem. That means the flamelet state were given Z and stoichiometric. So we have species mass fraction, and mass fraction when it is a flamelet, there is a function of chi and stoichiometric, and when there is a temperature, flamelet temperature and this. So this works nicely for two stream, and also it does not take into account any radiative heat loss, and these are some sort of a representative situation. Now another case could be where you have heat loss, that means a non-adiabatic situation. So the problem definition still remains same, that means you still split into two problems, one is mixing problem and another is the heat loss problem. So that means now you have to take into account one more extra variable, that is the enthalpy. I mean usually people take into account the enthalpy deficit or something like that, and then you find out the lookup table based on Z, stoichiometric and heat loss. Now heat loss is what is the enthalpy and the minus the adiabatic one. So it will be H minus Z stream 1, Z stream 2, and then your species mass fraction and temperature, they will become a now function of Z, which is evolving in the spatial coordinate system or the global spatial coordinate system, chi stoichiometry, which is a function of the Z, and that is also dependent on the spatial and the heat loss. So once we get this, then you can actually estimate your mean profile using the assumed PDF. Now different procedures are there or have been proposed, and literature to introduce these flamelets and considering the heat loss and all this. I mean these are again what we are doing here, discussion is the basic of all these things, but one has to look at the current literature where there are plenty of advancement has been made, because these things were proposed long time back and after then it has been modified. So these are, one can think about, these are quite standard methodology or approach for calculating non-premixed flame, the turbulent non-premixed flame, and there is a huge literature database which is available, and one can see how people come up with a different ways to define multi-stream problem and such. So we will stop it here today and continue this discussion in the next lecture.